So here is the topic. So our topic name is application of automata theory in game theory. So we are going to discuss this entire topic into two first. First, we will learn about what is the game theory, and secondly, we will learn how the automatas impact in game theory. So let's jump into what is first the game theory. So as the slide spells, the game theory that is a study of decision making in scenarios where the actions of multiple individuals or players determine the outcome is known as game theory. So it's interdisciplinary field of mathematics and economics. It is applied to stimulate situations where strategic choices are made by players to achieve their goals while taking into account the decision made by others. The concept of rational decision making formed the basis of early economic behavior models developed by mathematicians like John von Neumann and Oscar Mostrom in the early 90s. Over the time, game theory has emerged as a widely used tool in various fields such as political science, psychology, computer science, and economics. In the forthcoming slides, we are going to discuss about briefly the fields where you can clearly use the game theory with the help of the automata. So, the study of game theory involves examining formal models of strategic interaction between players. These models, called as games, consist of a group of players and a range of action each player can take, and a set of results that occur based on the actions taken. It is assumed that players in these games are rational and motivated by self-interest and always choosing the option that leads to the most favorable outcome for themselves. So briefly, where the entire topic is displayed in this point only. So by going further, we will discuss like what is the components of the game theory, and we will discuss like how like what is actually the game theory is. So if you go to the basic concepts in game theory, so we are having three major components here. First is player, second is strategy, third is players. So what is a player? We can tell it as an entity. In a game theory, a player refers to an entity or an individual that participates in a strategic interaction. Players are regarded as rational and self-interested, which means they aim to select the action that provides the most valuable option for themselves. So what it means by that? So basically, we are having an environment. In their environment, we are having some entities or it is an individuals which are self-interested or rational. By means, what we mean by the rational or self-interest is that they will choose on their own that is the most suitable one for them. So these are not motivated by some other person's will. They are self-interested, and these players we are having some sort of strategies when these player or whatever you call it is an entities. They are having some interaction with themselves, and during this interaction this interaction is called as game theory. And in this, meanwhile, we are having some sort of strategies. And the players have to choose the best strategies that is suitable for them. And this choosing, we can apply the automata here, the automata theory here. By applying the automata theory here, choosing that can be made much more simpler and much more efficient. And after that, what is the consequence? Suppose we are having a player, he has to choose something, and after that, whatever the consequence is called the players. And in the more or less, what is the we are going to see some more topics in this components of this game theory. These are called as an add-on to this game theory. So what is the first? First is the Nash equilibrium. Second is the dominant strategy. Third is the mixed strategy. So these are on the derived ones that we derived from the game theory components. That's the first major three components. So what is the Nash equilibrium? The Nash equilibrium is a concept that explains a situation where each player select the best strategy based on the strategies chosen by other players. So this is a strategy that is not solely decided by the player only, because he has to choose the best strategy for him based on the strategy of the other player. You can consider this like a chess game where the person is selecting something or he is choosing some strategy based on the strategy of the other player. So it implies that no player can achieve a better result by changing their strategy without assuming that other player will do the same. So here having a scenario here, this scenario tells us that A and B are two businesses vying for market share in a certain sector. So as you see here, depending on the decision that each firm makes, each number in the matrix indicates the reward for the company. As an illustration, if A advantages and B doesn't, then A makes a profit at 3 and B makes a profit at 0. Vice versa, if B makes an advantage and A doesn't, then B makes a profit at 3 while A makes 0. When both business decide to advertise and then game reaches the Nash equilibrium. If A advertises and B doesn't, then the same thing we have discussed before, but both of them advertisements they will get like 2, 2 or 1, 1, whatever the situation here it may be. So in that case only the Nash equilibrium arrives. So moving on to the next topic, we are having dominant strategy and mixed strategy. So what we mean by the dominant strategy is the player's best choice irrespective of other player's strategy. So here there is no need of the strategy of the other player. Like we are not affected by the strategy of the other player, but we choose the best possible strategy that is effective to us. And what is the mixed strategy? The mixed strategy tells that tells about the randomness, such as flipping a coin to decide between possible actions. The strategy can be used to ensure the other players cannot predict the player's action. So moving to the next topic, we'll see what is the types of games. So game theory classifies game into different types based on their characteristics and rules. So here we are having we mentioned 4 types of games. So what are they? Simultaneous games, sequential games, zero-sum games, and non-zero-sum games. So what do you mean by simultaneous game? In simultaneous game, players choose their strategy simultaneously in this kind of game without being aware of the decision made by other players. So what we discussed before, the person is choosing some strategy for himself but without the knowledge what the opponent is choosing. So this type of game is called simultaneous game, where we have the examples like Prisoner's Dilemma, The Battle of Sexes, etc., etc. What do you mean by the sequential games? Here the players select the plan sequentially in the form of game, each player selecting a choice after considering the decisions of the player before them. So these can be like in chess game or poker game, what we have discussed before. The person is choosing the game in a sequential manner after knowing what the opponents has selected for them. Now moving to the zero-sum games, majorly zero-sum game, what do you mean by that? These are like the poker games majorly considered as zero-sum games where we are having some sort of players and they will put their money. So one will gain and the rest will lose. So a player's gain in zero-sum game is exactly offset by the another player's loss. In other words, players pay off never add up to anything. The majority of gambling games are the example of these zero sum games. And we're talking about the non-zero sum games. The sum of players payers in the non-zero sum game can be either positive, negative, or zero. In cooperative non-zero games, participant cooperate to accomplish a shared goal. So what we call that we suppose we are having we can consider this like a Venn diagram. Suppose we are having a set of A, B, and A intersection B. So A is, shows the interest of person A's win. B shows the interest of person B person's win, and A and B shows the both side win-win scenario. While B can be, the set of B can be considered as the loss of the A. So that's all about the non-zero sum games. While you can give the example like Reasonable Dilemma, Ultimate Game are the example of non-zero sum games, and here you can there are two more games also. There is called as cooperative games and non-cooperative games. So what is cooperative games? You can tell it. Cooperative games are that way people propose the player can compete with another player to achieve an shared goal to achieve the goal. Where both of the players they will gain some rewards. If they will not do the things, some points will be deducted from them. While in non-cooperative games, there is no cooperation allowed. So the person has to complete the goal by himself only. If he is looking for help, then some points will be deducted from there. So that's all about the game theory. So now moving to automata and game theory. Automata can be very useful in game theory. As we previously discussed, what is automata and game theory? In the use of automata and game theory, here having some players. The player has to choose their strategy based on some strategies. Here this is not random. Person can choose any of the strategies, but think all it is. Person can choose out of some strategies. Person can choose the best possible strategy for him. And what is automata? The automata helps us in deciding which is the strategy you have to choose. That's all that is defined here. The automata can be very useful in game theory, particularly in the analysis of game where the strategies of the participants are interconnected. Systems that vary over time can be represented mathematically using automata. Automata learning has grown significance as a tool in game theory. Essentially, when it comes to machine learning, our ability to understand the tactics of other players. The process of automatically determining a model, the system's behavior from the observable inputs and outputs is known as automata learning. By examining their previous conduct and project, their future behavior, automation learning in game theory can be used to learn the strategies of other players in a game. Moving to the next topics. So games that can be modeled with the automata include the following. So we have just out of there is lots of games which can be modeled with automata. Here we just have some examples like Prisoner's Dilemma. What is happening here? Two players must choose whether to collaborate or defect in this classic game of game theory. So both participants will receive a little reward if they work together. The defector obtain a greater prize. The cooperator will receive nothing if one player cooperates while other fails. If both players cheat, they both subject to penalty. And automation with two other players can be used to stimulate this game, with each player having one the option to collaborate or defect. So that's how we can use the automata in Prisoner's Dilemma. We move to the second game. Here also same business dilemma. In this game also two players are driving towards each other. Both must decide whether to swerve or continue driving straight ahead. If both players swerve, there is no collision. They both receive a small reward. If one swerves and the other one not wins, player who doesn't swerve receives a larger reward, and the person who swerves receives a small punishment. If both players continue driving straight ahead, there is a collision. Both will get a last punishment. So here the automata also tells that we are having two options, either to swerve or to go straight. So this is all about the second game. And move to the next example, that is matching tennis. What happens here? The head or tail outcome of a penny is selected by two players simultaneously in this game. One player wins, the other player loses. If both players display the same face, if players face vary, the other player prevails. A two-player automation that allows each other to choose between showing heads or showing tails. So these are the same thing about what we have discussed in previous dilemma. Ultimate game. What is here in the ultimate game? A participant in this game can accept or reject another player's offer to divide the sum of money between them. The recommended division of the funds occur if the offer is accepted. Both player can nothing if the offer is turned down. So same the example with the prisoner's dilemma, same like them. So here you just see the examples of how the game theory can be adapted or the automata can be implemented to the game theory and make things more easy and suitable. Now let's move to the second topic, move to the forthcoming topic, the application of finite state machines in game theory. So here comes the real thing. We'll go to know like what is the application, how actually we can implement the automata. Like we are having three types of automatas here. Is the finite state automata, collaborative automata, and cellular automata. Here in this we are going to discuss about finite state automata and collaborative automata. Talking about cellular automata, it's still in this going phase. Scientists are doing their research on the cellular automata, so we are not having much more reference about that. So we are going to discuss about cellular automata. Sorry, we are going to discuss about finite state automata and collaborative automata, and we'll see what is the benefit of here, why we are shifting towards the cellular automata. Talking about finite state automata, what is the major problem in finite state automata? We are only focusing on finite state machines or regular languages. If any other language means we can't able to define that. That's the problem of finite state automata. Collaborative automata is same like finite state automata. So what is the plus point there? So the plus point is it is much cheaper than finite state automata. If we are talking about budget, it is less costlier than finite state automata. That's why in 2005 we moved towards collaborative automata, and we're gonna see now like how with the help of automata like finite state automata and collaborative automata, and we'll see just application of collaborative automata because they both are the same. The collaborative automata can be considered as a solution, as a solution of an existing solution. We'll see how finance automata is checking this. So talking about the application, so we discussed already like what is we got the overview about what is finite automata, how it is helping. So let's talk about the application. In game theory, finite automata are employed to stimulate player's action and strategy. The input reflects the action the player can do in each step. The state of the finite automata indicates the various possible game situation. The transition function specifies the outcome they follow from each combination of player establishes the game's rules. Game theorists can forecast game results and pinpoint the best player for each player by examining the invention automator's behavior. So here you are having three types of games. There is a sequential game and repeated games and evolutionary game. And finite automata model, sequential game with each state representing a game stage and transition defining possible actions and outcomes. While in repeated games, finite automata models repeated games with space representing the game history and transition defining possible actions or outcomes. In evolutionary games, finite automata models which states representing the current strategy distribution and the transition defining the probability of adapting to the new strategies. So that's all about the application of finite state machines in game theory. Let's move towards how it actually works. So here we are having an example where we know that the finite state machines are represented by four symbols, that is R equal to S, I, F, and S naught, where S is the set of states, I is an input symbol, F is the transition function, S naught is the initial state. So here what happens, we just give the example of 10 player prisoner dilemma. So what happens here, first two players, so we are having the initial state as in C1, or we can call it as in C. So first player selects C as an initial state. With this round, none of the other two players select C. Total number of cooperator will be 0, excluding the player itself. Transition 0 will change the current state from C1 to D1. In the following round, the agent will play D since the current state is D1. Assuming the one player is cooperated, therefore the total number of cooperator will be 1. The transition 1 changes the state from D1 to D1 itself. In the next round, the player will D again. So that's all about. We just see the example of how we can define the finite automata in the case of main player prisoner's dilemma. So what's the problem here? That using finite automata as a modern language has its own limits, and finite automata are only capable to regular languages, as we have discussed before. So that's why we move towards context-free grammars and the PDS. So modeling of games with context-free grammars. So we can give the example of poker here. The game of poker is one of the examples of a game that can be modeled with the PDA. Each poker player receives a hand of cards, and based on the situation of their hand, the cards on the table, they play the base. The beginning state of the game is the hand of the card dealt to each player, and each succeeding state is the outcome of the player section, which can be visualized as a context-free grammar. The game of name is another illustration of a game that may be modeled with an PDA. Each player in a game name takes turn taking objects out of the various objective fields. The files arrangement can be thought of the game's beginning state, and each succeeding state as the outcome of the player section in the context-free grammar. PDS, or what you call it, push-down automatas can be helpful in game theory because they can employ context-free grammars to capture the recursive structure of games. The interesting, the best playing styles for each participant in the game's potential outcomes can be all discovered by researchers by examining the PD. So move to the applications because we just see the overview, like how the financial automatas are. Financial automatas can be used in the case of game theory, and how the context-free grammars or the push-down automatas can be held in the automata in the game theory. So now just move towards the application of adaptive automata. We also know that we have to move from financial automata to application of adaptive automata. So why we are choosing this? Generally, the adaptive automata have a cheaper implementation compared to the other mechanism. That's why we are using the adaptive automata. The adaptive automata based on devices have been presented as a powerful tools for defining complex languages. These are the following points why we are choosing this. The accepting procedure performed by an adaptive automation is run efficiently due to their structure, which is based on finite state or structured push-down automata. So basically, it is combining both the finite state and push-down automata. Adaptive automata can handle context dependencies in a strict synectical way without the aid of auxiliary semantic procedures. The structure of adaptive automata is extended to implement transducers, allowing the combination of fast base as a side effect of passing sentences. Adaptive automata can be considered as an alternative existing solution of natural language processing. So here we just got an overview why we are using the automata, and why what is the problem with finite state automata, and why we are using the adaptive automata. So here is the something like automata learning and game theory. That is like the fields where we can actually apply or game theory with the automata is being used. So game theory and automata are effective tools with many diverse applications. Researchers, practitioners may model and analyze complicated systems, create effective algorithms on how people and groups behave in various settings by using these tools. In economic section, political section, psychology section, artificial intelligence, in lots of section we can use it. So here this is just an example like how we are using it. Let's just give an example of economics. Economics makes considerable use of game theory to stimulate and examine choices made in condition of competition. Considering the different economic phenomena, including market behavior, pricing, tactics, and the effects of changing politics on the market, can be aided by game theory. Supply chains, financial markets, and the transportation system may all be modeled and virtually tested using automata theory. Same thing, like just get the example of some points about how it's been useful in the economic section. Same with the political section and artificial intelligence section. So what will be the future directions of this game theory? It's the help the automata theory. So here you can give some example, give some points like the new modeling techniques, the practical application, multi-agent system, complexity, and scalability. Talking about new modeling techniques, automata and game theory are being used increasingly frequently by researchers to simulate and evaluate complicated systems. For instance, scientists are investigating the use of probabilistic automata to describe stochastic and uncertain systems. Talking about practical application, in the field of economic politics engineering, there is growing interest in applying automated game theory to address real-world issues. For example, in order to create effective transportation system, allocate resources for healthcare, and manage natural resources, researchers are looking into the use of game theory in these areas. Talking about multi-agent systems, researchers are investigating how to describe and evaluate multi-agent systems where several agents interact with one another to fulfill their goals. Using automata and game theory, robotics, autonomous driving, swarm intelligence application fall under this category. Talking about the complexity and scalability, the techniques that are scalable and applicable of handling large-scale systems are required when the system complexity rises. Researchers are investigating how automata and game theory may be used to create effective algorithms for deconstructing and improving complicated systems. So that's all about the future directions of this game theory, the automata theory. So moving to the conclusion section, game theory and automata are significantly disciplines of research with numerous applications. Game theory studies how strategic decisions are made in competing circumstances, whereas automata theory studies the mathematical models of computing and communication. Together, these disciplines offer strong tools for stimulating and analyzing complicated systems, creating effective algorithms, and learning how people behave in various situations. Several fields, including economical, political science, engineering, artificial intelligence, automata, and game theory. So that's all about the entire topic. Thank you.